In the spring of 1956, John von Neumann, who's known for a wide range of contributions to quantum physics, game theory, and the atomic bomb, lay in a hospital in Washington, too weakened by cancer to work. One day, a handwritten letter reached him there, sent by Kurt Gödel, the logician famous for his incompleteness theorems. In this letter, Gödel wrote the expected things, well wishes, and hopes for recovery, and then he posed what seemed to be a simple question. Is finding an answer really any harder than checking one? Welcome to Voyager, where we investigate the biggest unsolved mysteries in math, science, and engineering. Today, we're exploring P versus NP. Gödel didn't know it yet, but he'd just written down one of the biggest unsolved problems in computing, and he'd reached it a decade and a half before anyone else would even think to ask. But there's no record that von Neumann ever replied. He died less than a year later, in February 1957. And the letter itself went missing for 33 years. So what exactly did Gödel's question mean? Consider a delivery driver with a list of stops and a limit on the time to complete those stops. For example, a route must not take more than 4 hours. To confirm a proposed route stays under that time limit, you can add up the time to complete each leg and compare the sum to the limit. This is one example of a problem that's easy to check given a proposed solution. However, it's not as easy to find such a route from scratch. To find a route through a list of cities that stays within a time limit, you might have to test or search a large number of possible arrangements. And the number of possible arrangements rapidly increases with each additional city added to the route. If a driver has to stop in 5 cities, there are only 12 different routes to test. But if the driver has to stop in 60 cities, then the number of possible routes is roughly 7 times 10 to the 79th power, which is comparable to the number of atoms in the observable universe. Even if a computer could test 1 trillion routes every second, it would take longer than the age of the universe to test them all. So what does that mean? Is the fact that some solutions, even when trivial to recognize, are hard to find in the first place a feature of the problems themselves? Or has the method to quickly solve these problems just not been discovered yet? Stated plainly, this is what the P versus NP problem is. It asks, if a problem solution can be easily checked, can that problem be easily solved? It makes sense that finding an answer should be harder than checking one, and according to polls of experts who study the problem, almost 90% believe that that's the case, that checking and finding are genuinely distinct, that easy to verify does not imply easy to solve. But there's actually no proof. No one has ever shown that a shortcut from checking to finding cannot exist, and that is what makes this problem so interesting. It's a fundamental question in computer science, and today there's $1 million waiting for whoever can answer it, as it's one of the 7 problems the Clay Mathematics Institute named as the most important problems of the Millennium. So mathematically, what does it mean for a problem to be easy to solve? Before I answer that, if you're enjoying this video, please like and subscribe. I really appreciate your support. If you have a group of people to pair up, say organ donors to patients where only certain matches are allowed because the blood types have to be compatible, ages have to be close, and medical histories have to line up, how do you form as many valid pairs as possible without using anyone twice? For a handful of people, the pairs can be quickly worked out by hand. But with just a few more, the number of possible arrangements climbs quickly, and by a few dozen, there are already more possible pairs than a computer could check one at a time in 1 billion years. So with larger sets where you don't want to test every combination, how can you make those pairs most efficiently? Well, that's the problem Jack Edmonds set out to solve, and in the spring of 1965, the Canadian Journal of Mathematics published his answer under an unusual title, Paths, Trees, and Flowers. In this paper, Edmonds claimed that he had found a good algorithm for it. But before he could present it, he hit a strange gap. He wanted to claim his method was good, but no one had ever said precisely what a good algorithm means. So, in a digression in his paper, he made the first clear definition of what this means mathematically. An algorithm is good, he argued, when the number of steps it takes to solve a problem grows like a polynomial based on the size of an input n, for example n squared or n cubed, rather than growing exponentially, such as 2 to the power of n. An algorithm where the number of steps grows at the rate of n squared has 2,500 steps when the input is 50. But an algorithm where the number of steps grows exponentially would have 2 to the 50th power, or about a quadrillion steps for the same input. This difference between polynomial and exponential scale problems is the difference between a problem being easy or hard to solve. The polynomial scale problems run in polynomial time and are therefore called p-problems. P-problems, for example, sorting a list into alphabetical order or simple multiplication, are easy to solve, easy to check, and are sometimes called tractable problems. But some problems aren't easy to solve. Like the case of the delivery driver, as the number of cities increases beyond a few dozen, the problem quickly becomes impossible to solve, even though it's easy to check a provided solution. And this type of problem, where the steps to find a solution expand rapidly with increase in problem size, are defined by non-deterministic polynomial time. Imagine a machine that, faced with all those possible routes, did not have to try them one by one. A machine that could somehow guess the right route in a single step, and then simply verify it. Such a machine does not exist. It's a theoretical device called non-deterministic that's allowed to make a lucky guess every time. So NP is the class of non-deterministic polynomial problems that this imaginary lucky guessing machine could solve quickly. This class describes problems whose proposed solutions can be verified in polynomial time, but finding the solutions from scratch often requires searching through vast numbers of possibilities. Every P problem is also an NP problem. If you can solve something quickly, you can certainly check it quickly. The question is whether the reverse is true. Are all these NP problems, the ones that look impossibly hard to solve, actually solvable in polynomial time? And we just haven't found the algorithm yet. If the answer is yes, then P equals NP, and the salesman or delivery driver problem has a fast solution waiting to be discovered. But no one has ever found one. And surprisingly, that same gap of easy to check and apparently impossible to solve started turning up everywhere, from circuit design to protein folding to Candy Crush. And in 1971, two independent researchers proved something strange, that all of these seemingly unrelated problems were underneath the same problem. So how are scheduling an airline crew and clearing a board of Candy Crush actually the same problem? The answer to that came from a man his own university had just let go. In 1970, Berkeley's mathematics department denied Stephen Cook tenure, a decision one of its own professors, Richard Karp, would years later call the department's everlasting shame. Cook moved to the University of Toronto, and within a year from that new desk, he proved something exciting in computer science. Cook started with a single problem called satisfiability. A satisfiability problem is a list of true or false conditions, all of which have to be met at once. Think of it as a set of switches, each either on or off, and a list of rules about them. This switch and that one can't be both off. If this one's on, that one must be on too. The question is simply whether there is some setting of all the switches that satisfies every rule at the same time. For a few switches, you can work it out quickly. For many, the number of possible settings doubles with each switch added, and checking them all becomes hopeless. Satisfiability is an NP problem. Hand someone a proposed setting and they can check it instantly, but finding one from scratch seems to require searching. And what Cook proved was that satisfiability is not just one NP problem, but that it's actually all of them. Take the job of scheduling exams. A university has a set of exams to place into time slots, and a constraint. Ideally, if a single student is enrolled in two of them, those two exams cannot share a time slot, or that student would have to be in two places at once. With hundreds of exams and many thousands of students, finding a conflict-free schedule is hard. It's an NP problem. Now look at another problem, a coloring map. Given a map with different regions and asked to color them so that no two regions sharing a border get the same color, what is the fewest number of colors required? This is also an NP problem. And these look like unrelated puzzles. But, as Cook showed, they're actually the same problem. Let each exam be a region on a map. Whenever two exams share a student, draw those two regions touching, sharing a border. Let each available time slot be a color. Now, the map coloring rule, which says that neighboring regions must differ in color, is the same as saying that two exams with a shared student must land in different time slots. So the solution to the coloring map problem ends up being a valid exam schedule. Solve one, and you've solved the other without any further work. This type of translation, of turning one problem into another, is called a reduction. And what Cook proved is that every single problem in NP, the traveling salesman, scheduling, map coloring, as well as thousands of others, can be reduced in this way to satisfiability. So if anyone ever found a fast algorithm for solving that one problem of switches and rules, the translation would result in a fast algorithm for everything in NP. The whole class would be easy to solve, and thus equal to P. And Cook wasn't the only one working on this. Actually, the exact same result arrived at the same time, independently, from the other side of the world. In the Soviet Union, working in isolation and with no knowledge of Cook's paper, a young mathematician named Leonid Levin had proved essentially the same thing. He had been studying brute force search, the mindless trying of every possibility, and asking whether, for certain problems, there was a more efficient way. And he arrived at the same universal class Cook had. And then, a year later, Richard Karp made the conclusion even more compelling. Karp took 21 of the most famous unsolved problems in computing, scheduling, packing, map coloring, the traveling salesman among them, and showed one after another how each could be reduced to the others. He demonstrated in case after case that these were not separate challenges. A fast algorithm for any one of them would be a fast algorithm for all 21. Solve the salesman, and you've solved scheduling and protein folding and circuit design. And it would turn out, based on research in specific cases, you would also solve Candy Crush, Minesweeper, and beat Tetris. And these universal problems have a name. They're called NP-complete. An NP-complete problem is one that every other problem in NP can be reduced to. But not every problem in NP is NP-complete. Remember that easy problems, matching, sorting, root finding, are in NP too, since anything you can solve quickly, you can also check quickly. NP contains a whole range of difficulty from the trivial to the universal, and the NP-complete problems are only the hardest problems in NP. And between the easy problems and the universal ones, there seems to be a middle ground. A few problems in NP have resisted every fast algorithm anyone has tried, and yet no one has managed to show that they're universal either. So these are called NP intermediate problems. The clearest example is factoring. Given a large number, find the prime numbers that multiply together to produce it. Checking a proposed answer is easy, you just multiply the factors back, but finding them is hard enough that much of modern encryption is built on this difficulty. But factoring is not believed to be NP-complete, falling in this region for problems that are harder than the easy problems, but not universal. But what about problems that are not easy to check? The traveling salesman problem, as we've defined it earlier, was finding a route within a time limit. And this is a useful example of NP because this problem is easy to state and easy to check. But that's only a very specific case of the problem, a yes or no case. What about if you ask instead for the shortest route? Not whether a short one exists, but what is the absolute best route? Now it's not even easy to check. Hand someone a finished route and they can measure its length, but they can't confirm it's the shortest, because to know that, you'd have to confirm that no other route is shorter. This version cannot be verified quickly at all, which puts it outside of NP. It belongs to a wider class of problems that are at least as hard as everything in NP without being checkable themselves. And these are called NP-hard problems. And NP-complete is the overlap of NP and NP-hard. And the complexity classes only expand from there. What if you ask, in a game of chess, will the first player win? Here, even quantifying an answer is hard. A single move tells you nothing by itself because whether a player wins depends on the other player's reply, and the reply to that reply, down every branch the game can take. These regions above NP have been mapped and named P space and then XP time, for example, each demanding more than the last. I'm not going to get deeper into this here, except to say that at the very top is the halting problem, the problem no machine can solve at any speed. So, getting back to P versus NP, a fast solution to any single NP-complete problem is a fast solution to every problem in NP at once, making P equal NP. And yet no one has found one of these solutions. So if these problems are so hard and all of them are the same hardness, then they should be appearing in the real world as unsolvable. But they aren't. Every day, engineers schedule airlines, route delivery fleets, and lay out the wirings of microchips, solving, in practice, the very problems theory calls impossible. We'll get into how this works, but first, if a single fast algorithm would unlock everything, why has no proof even gotten close? Karp's list had turned an abstract question into a sensation, and in the early years after the question was defined, many expected an answer within a decade. But after several years and many failed proofs, no one was getting close. Then, in 1975, Robert Solovay, a set theorist with no particular stake in the new field of computational complexity, added his name to a short paper along with co-authors Theodore Baker and John Gill. Although the title of this paper was flat and technical, relativizations of the P versus NP question, this work did something new. Instead of trying to solve the P versus NP problem, they asked whether the standard proof methods could even work. Before 1975, mathematicians hoped to solve the P versus NP problem using diagonalization, the same mathematical technique Alan Turing used to prove the undecidability of the halting problem. Diagonalization proofs treat computational machines as black boxes. Therefore, because they don't look at the inner code, any proof engineered by diagonalization remains valid if you attach an arbitrary helper, called an oracle, to the system. This property is called relativization. So Baker, Gale, and Solovay constructed a thought experiment. Imagine handing a computer an oracle that can answer any single yes or no question about a hard problem instantly and for free. When a machine is given access to an oracle X, its complexity classes are written as p to the x and np to the x. The computers should behave identically whether or not any oracle is present. But Baker, Gale, and Solovay showed that different oracles give different answers. They proved that there exists an oracle A such that p to the a equals np to the a, but there also exists an oracle B such that p to the b does not equal np to the power of b. According to relativization, that cannot happen. The computers should give the same output no matter what is inside the black box. And this was the first proof barrier, and it's called the relativization barrier. Any successful proof could not come from just looking at the inputs and outputs. Instead, it would have to come from looking inside the algorithm. One way to do this is to construct an algorithm from a small circuit. If an algorithm can be constructed from a small, fixed arrangement of basic logical operators, then that algorithm is within P. The difficulty with this approach is that it's also a type of search problem. You have to rule out a vast number of small circuits that don't work in order to find one that does. But there's a shortcut. What if you could find some property, let's call it property X, that all hard problems have and easy problems do not have? This property or pattern would be what makes hard problems hard. And two constraints on this property are that it must be easy to detect and it must be true for most random functions. This method is called the natural proof method. However, when applied to the P versus NP problem, it creates a logical paradox. A property that is common and efficiently checkable is exactly the kind of test that can tell a truly random function apart from one that only looks random. Like, for example, the pseudo-random functions that modern cryptography depends on. The security of those constructions relies on the assumption that no efficient test can reliably distinguish their output from true randomness. A successful natural proof would be precisely such a test. So any proof based on this method would simultaneously show that the cryptography believed to be secure is breakable because we would instantly be able to tell the difference between truly random data and pseudo-random data. So until someone finds an algorithm that instantly cracks all of cryptography, which would anyway mean that P equals NP, this method is a dead end. So that left one avenue, and it initially showed real success. Some proofs sidestep machines and circuits and translate logical statements into algebra by rewriting a Boolean formula as a polynomial over a larger number system. But when Scott Aaronson and Avi Wigderson extended the oracle idea of 1975 to match the algebraic methods, again, two different mathematical universes were returned. Algebra alone is logically blind to the actual difference between P and NP. And this barrier, called the algebrization barrier, rules out advanced algebra because polynomials are too flexible. They smooth over the precise, discrete, structural differences that separate easy problems from hard ones. So, any proof that could finally settle P versus NP must avoid all three barriers at once. It cannot use standard computer science simulations because of the relativization barrier. It cannot use standard counting and logic because of the natural proofs barrier. And it cannot use standard polynomial algebra because of the algebrization barrier. And as of 2026, no known technique clears all three. If P versus NP is so resistant that the field can prove its own methods inadequate against it, how is it that these hard problems are getting solved at all? One application of the traveling salesman problem is in optimizing the production of computer chips. In this scenario, a laser travels across a chip, vaporizing connections to be cut in the final configuration. The traveling salesman problem in this application then becomes minimizing the total travel time of the laser, and the cities correspond to the locations of the connections to be cut. In 2006, William Cook, unrelated to Stephen Cook, who discovered the satisfiability NP complete problem, was part of a team that had been working for years to build a program that could solve the traveling salesman problem for this application. The traveling salesman problem, as we've seen, is one of the standard examples of NP-complete problems that would be nearly impossible to solve for a large number of inputs. But Cook, along with David Applegate, Robert Bixby, and Vasek Vattel, thought they could solve it. The challenge was, a computer chip has 85,900 connections. Researchers at Bell Labs began working on the problem, and in 2006, the team watched their program, called Concorde, return a result. The result was a route, and it was provably the shortest route through 85,900 cities. And this perfectly illustrates the paradox of modern computing. Every day, international airlines assign flights to crews and routes, and shipping companies map paths for thousands of deliveries. These are all theoretically impossible NP hard problems, but planes still fly on schedule. The work gets done because real-world programs don't look for mathematically perfect algorithms. They settle for answers that are simply good enough, found fast. The tools that do this are heuristics and approximation algorithms. They work because the true hardness of an NP problem is a claim about its absolute worst case, the single most difficult engineered input possible. But ordinary, real-world problems are not the absolute worst cases. Real-world examples have specific properties that actually make them easier to solve. Because of these properties, solvers can routinely approximate cases containing millions of inputs. This gap between the theory of problems that are impossible to solve and the reality that we basically solve them every day was finally explained looking at how minor random changes affect a problem. Mathematicians proved that an optimization tool called the simplex method, which is exponentially slow in theory, runs near linearly in practice because tiny real-world perturbations of the input actually make the algorithm fast. This is because the worst-case problems are incredibly fragile. They require every single constraint to be positioned at precise, exact angles to maintain the difficulty. But in the real world, data is never that precise. It's inherently filled with tiny random imperfections. For example, a delivery truck might be delayed by 3 minutes, or a component costs 2 cents more than expected, or a physical measurement gets rounded off. And these random imperfections cause the precise difficulties to collapse. But while we can approximate real-world NP problem solutions, we're still not able to truly answer the P versus NP problem. And even if clean proof is found, it might deliver far less than we expect. Donald Knuth, who has been called the father of the analysis of algorithms, has stated that he suspects P actually equals NP, but he expects the proof to be non-constructive. That means that the proof would establish that a fast algorithm exists without giving us any instructions on how to actually build it. Or that the algorithm might run in polynomial time, but it might be a polynomial like n to the power of 50, which would be practically useless for more than a few dozen inputs. To map what an answer would truly mean, computer scientists Russell and Pagliazzo divided the possibilities into 5 hypothetical worlds, any of which we might live in. He called them, rather whimsically, algorithmica, heuristica, Pessoland, minicrypt, and cryptomania. And these 5 worlds are defined by different assumptions about P versus NP, and they illustrate how the relationship between P versus NP and the existence of one-way functions impacts cryptography, technology, and philosophy. The implications in this 5-world framework reveals why cryptography needs far more than a simple proof that P does not equal NP. Secure encryption not only requires P does not equal NP, but also requires that problems are hard on average, not only in the rare worst-case scenario. So although you might see people say that a proof of P versus NP would break cryptography, it's a bit more nuanced than that. But as we saw with Concorde, the traveling salesman problem with 85,900 cities, computers can sometimes force answers through sheer scale. And in 2016, researchers settled a long-standing puzzle called the Boolean Pythagorean triples problem, using a satisfiability solver. And in solving this problem, they produced the largest mathematical proof in history. The supercomputer generated a machine-checked proof that was 200 terabytes long. For context, that's equivalent to reading War and Peace 67.5 million times. And ultimately, the supercomputer used all 200 terabytes of data to answer a simple yes-no question, and the final answer was no. This proof solved one problem, but it left researchers with a new question. What does it mean to know a theorem is true when the proof is too massive for any human being to ever read? Ultimately, solving P versus NP really comes down to 3 questions. Are P and NP equal? Can that be proven? And would the answer change anything? In pursuit of these answers, classical proof has stalled. But what about modern approaches? I looked into 3 newer approaches to P versus NP, and even wrote a whole video chapter on them. It was too much to fit here without losing the thread, but I've posted the full recorded extended video on my Patreon. If you want to see how mathematicians are currently attacking the problem, that's where to go. And that's really what my Patreon is for. Every video you're watching is made by me from scratch, from researching, writing, filming, and editing, and each step can take days, sometimes weeks, to get right. These videos will always stay free, but the tangents and deeper material that don't make it into the final YouTube cut will be on my Patreon. Your support also will help me bring in the talent to publish videos a lot faster, as well as elevate the production quality. The link's below. Thank you for your time, and I hope you'll join me on my Patreon. Getting back to the story. So what would a proof even look like? And what would it change? In 1989, Joris Hartmanis, a computer scientist at Cornell, sat with a translated copy of a letter that had been written 33 years earlier and recognized how important the question Gödel had proposed to von Neumann was. And versions of this question have been appearing for centuries. Leibniz wanted a universal calculus that could settle any dispute in computation. Hilbert wanted to mechanize proof itself. Turing, in 1936, answered a piece of that ambition by showing that some yes or no questions can never be settled by any machine at all. Gödel's 1956 letter is the successor to Turing's result. Not can this be decided, but can it be decided feasibly? And stripped of its mathematical formalism, the P versus NP problem asks whether creation is different from recognition. Consider a mathematical proof. Following one line by line, checking that each step is valid, is something a great many trained people can do. But producing that proof in the first place is rare, and the field gives the highest honors to the people who can. P versus NP asks whether that gap is real or only apparent, whether finding the proof is fundamentally harder than verifying it, or whether the difficulty is an artifact of not yet being clever enough. Theoretical computer scientist Scott Aaronson made a philosophical argument for why P cannot equal NP. In a now famous post titled Reason to Believe, he wrote that if finding were no harder than checking, if P equaled NP, then, in his words, everyone who could appreciate a symphony would be Mozart, everyone who could follow a step-by-step argument would be Gauss, everyone who could recognize a good investment strategy would be Warren Buffett. The capacity to recognize a good symphony or a good proof would carry the same power as the capacity to produce one, and there would be no special value in creative leaps. In spite of this, there's a piece of folklore attributed to John Hopcroft. Even if one works basically all week trying to prove P does not equal NP, one should set aside Friday afternoon for trying to prove P equals NP. The takeaway being, let's dare to think crazy thoughts and explore crazy directions, trying to develop crazy new techniques on Friday afternoons, and perhaps beyond. But suppose the consensus is right and P does not equal NP. What kind of universe would that describe? In a 2005 survey, Aaronson examined every physical method anyone had ever proposed for shortcutting these problems. His proposal was to treat the intractability of NP-complete problems as a law of nature, like the impossibility of perpetual motion. The 200 terabyte proof from earlier is already an instance of this. A result checked mechanically and proven to be true, but impossible to be read in full by a person. It can be confirmed, but it cannot be comprehended. And systems like Google DeepMind's Fun Search now make verifiable mathematical discoveries by search. If finding ever became as cheap as checking, what would be at risk is not the answers, but the understanding of them. Comprehension as the last human act that does not reduce to a search. So, if discovery is only an algorithm waiting to be optimized, if finding is really no harder than checking, then is there such a thing as creativity? Or is invention only a search not yet automated? If this is the kind of content you want to keep seeing, subscribe. On this channel, I investigate unsolved questions in math, science, and engineering. And if the story of the P versus NP problem pulled you in, you might like my recent video on another one of the unsolved Millennium Prize problems. It's on screen now. I'll see you in the next one.